Hi, I'm Norm Vimoy with Xylem Flight Pumps. We'll be demonstrating how we're going to pull pumps from Little Suwannee Pump Station today. I brought a little demo pump with me to demonstrate what we're going to be doing once we open these hatches and lower the crane into the hole. A chain sling just like this one is hooked up to a larger full-size version of the pump down in the wet well. This latch here, can you hold this for me? There's a string that's connected to the top, and when we lower the crane down, it's going to lower this chain sling device to a point where we can loosen the string, and then this will grab the chain hoist, and then when we lift the pump or lift the crane back again, it'll be able to pull the pump out of the well. And then when we lower it back in, when we go to put it back down, we'll hold the string tight, we'll loosen it, and then he'll be able to lift it right back up again. All right, kind of give you an idea of what's going down, up on down at the bottom. There's a base elbow, the same size as the one over there. And as the pump is lowered, it's lowered at a slight angle, and then it sits down on the base elbow like that. And then when we lift it up, it comes up following the guide rails the same way. We're getting ready to actually pull the pump. You can see on this example, this crane has a safety latch on it so that this can't fall off while we're lifting it up and down. We're going to hook it onto a rope, and you'll see that here in a minute after we open this hatch up. We're going to lower it down part way, and then we're going to take a video of what we have to do as far as turning off the breaker and the controls before we continue any further. We're going to hook up the rope connected to the chain sling before we go down and pull it through the grip eye that's connected to the crane hook. All right, so he's going to let that follow the rope down till it grabs that chain sling. Before we go to work on any motor, one of the first things we have to do is make sure that the power's disconnected. For pump one, we're going to turn off pump one's breaker. We're going to turn off the hand-off auto switch. On the PLC, you go to the pump page and you put the pump in off and out of service, and then it'll re-display like this, showing that the pump is off and now no longer available, out of service. Once we do that, then we know we're good to pull the pump.
Doesn't like pulling on the side. It doesn't like pulling on the side and waiting.
We're going to be adjusting the impeller, or going over the adjustment of the impeller. What you're looking at is looking through the discharge of the pump. You can see where the impeller sits near the bottom insert ring, and we're going to be adjusting that to about 0.5 millimeter using a 14 and a 17 millimeter Allen wrench. And we'll go over that procedure, but you're not going to be able to actually see it. So we're showing what we're adjusting in advance. We've took the 14 millimeter wrench, and while I was holding the impeller, Garrett loosened it using a 14 millimeter wrench and removed the impeller bolt. Now that the impeller bolt's removed, we can take a 17 millimeter wrench and adjust the impeller colic and move the impeller up and down to get our 0.5 millimeter clearance off the bottom plate, the insert ring, the one that we showed you in the previous video. So now we're ready to adjust the impeller down onto this 0.5 millimeter feeler gauge. So I'm going to stick it underneath the where the impeller meets the base plate, and then Garrett's going to take that 17 millimeter wrench and he'll probably turn it a couple times to get it down to where it makes contact. Okay. Yep, and I can still pull it out, so that's a good thing. All right, once we do that, then we'll put the 14 millimeter impeller bolt back in and tighten it to torque. And then once that's in, you don't torque the colic, you torque the impeller bolt, and that's what holds everything in place. So we'll put the impeller bolt back in, torque it, and then we'll be done with this impeller adjustment. This is the pump data plate. It has all the pump information on it, like we go over in the O&M manual. The first part is your pump model number, the motor version, which is 095, and then the serial number, which has a S designation in front of it. The S just means it has something special on it. On these pumps, the special item is the 498 millimeter special trim impeller. There's the three-phase 60 hertz telling you what type of motor it is. It's 78 kilowatt or 105 horsepower. The speed of the motor at 60 hertz is 1775 RPM, and it has a S1 duty rating, which means that it's made to operate at full load amps, but not more. And the reason it's S1 is because it's a VFD inverter motor. You still have the combined service factor of 1.15, including the pump and the application. The motor temperature rating is 40 degrees centigrade, which means it can operate in ambient temperatures up to 104 degrees. The voltage of this pump is 460 volt. It has a delta winding motor, and that's important for when you're making the connections inside this terminal box. It's 125 full load amps. The cosine theta for the motor is 84.84, and that has a lot to do with its efficiency rating. The thermal protection level is 1111, and it's class H insulation with the international standard code of 60034.1 and an IP rating of 68 for continuous submergent. Its submergence maximum is 20 meters or 68 feet, and it weighs 850 kilograms or a little bit more than 2,000 pounds. Down here is the FM plate, which just means it's explosion proof rated according to Factory Mutual, which is pretty standard in the United States for explosion proof applications. We've got the pump out of the hose, so one of the things we're going to do is check the coolant fluid in the pump. It's glycol, so he'll open carefully the top section, making sure that it doesn't have any pressure on it. Just so you know, we already opened it to make sure that that didn't have pressure on it. Then he's going to stick something in there to check the level in it and make sure that the glycol should be up to somewhere around the threads on the bottom of that hole. Whenever we pull the plug, we have to, as a practice, replace the O-ring on it, because when you compress it, you could potentially damage the O-ring. So it's better just to put a new one on every time you check it. And it was full, it's fine, so we're going to put it back in the hole. Okay, so what he's checking now is the stator housing. The stator housing shouldn't have any fluid in it whatsoever, so he opened up the stator housing to make sure there's no fluid in it, no sign of any leak. There's no oil in the stator housing or anything, so it should be dry. Over time, it will accumulate some fluid just because seals vibrate, so you do get some pass through in there, and every once in a while you have to drain it and then do a seal test on it where we pump up the housing to about 15 pounds and make sure it holds. We're here at the diversion structure at Little Suwannee Pump Station in Gwinnett County. I'm standing on top of the diversion box on a gravity line that comes through this area. And they built this diversion box on it with two gates, one to block the flow from going to Yellow River and one to allow the flow to go to the Little Suwannee Pump Station. Right now, all the flow is going to Little Suwannee Pump Station. And you can tell by these the shaft on this valve that it's open and the other shaft is closed. This is the receiving manhole. This is the manhole that the diversion structure diverts into. It's at a lower elevation than the gravity line going to Yellow River, so the flow naturally comes this way. And then the pump station itself is lower than this receiving manhole, so it goes through the grinder vault and into the wet well. If it backs up at all, it'll start backing up into the storage tank, and we'll take a look at the storage tank next. We're at one of four entrances into the storage tank. The storage tank is at a higher elevation than the gravity line coming from the receiving manhole, so that if the flow backs up, it'll start filling the storage tank. The gate going to the diversion box or from the diversion box to the station can be closed, and they can actually use this storage tank to empty the force main and store the volume of the force main in this storage tank if they allow it to go back through the pumps and fill up this area, allowing them to do emergency repairs on the force main. What you see here is a control station for the plugs, the 480 volt plugs for the fans that they have to use to ventilate if they ever have to go into this structure. It's confined space. There are multiple ways in and out, but it's difficult, and there's no real airflow unless the fans are running. It is vented, but only if you add the fans. So they have to plug in the fans, and you'll see there's plugs at two of these entrances where they can add the fans, and they also put concrete pads for them to place the fans on so they can drop the hoses in to keep it ventilated. And they can force the air in or out, and those big candy canes allow the air to circulate when they do that. After the receiving manhole, by gravity, the flow goes through this grinder vault. The grinder vault has a gas detector in it because it has a stairway to go down into it, and there's a go no go light. However, the purpose of that go no go and gas detector is really not for people. It's to make sure that the fans don't run if there's an explosive atmosphere. So you should be using your own personal gas detector to enter this space and follow the confined space entry regulations when you go in and out of this grinder vault. On this grinder vault, the flow comes in through this gate, which is controlled by the PLC. And the reason it's controlled by the PLC is if we do fill the storage tank, we want to be able to meter the flow back or hold the flow in the storage tank for a while we pump it down at a controlled rate. And then each grinder has its own gate as well, so we can block it off and pull it for service or force the flow in one direction or the other for any reason. However, each grinder is capable of handling the entire 4 MGD for this pump station. Hi, we're at the float terminal box with the intrinsically safe relays and the mission terminals as well. The mission is hooked to its own float and does not go through any powered relays, so it hooks directly to the mission RTU. So if all else goes wrong, the mission will be able to tell if there's a high level, even if there's no power here. For the floats, when they hook it up, they're all hooked up normally open. And normally open means that when the float's hanging straight up and down, the gray and the black wire are not connected. So right now our ohm meter is showing no connection. So when the float turns over, now it's showing a connection. So do that again. Here we go. No connection, connection. So as the water rises, the switch in the float closes, completing the circuit and turning on the pumps. Now these floats are only used as a backup to the level transmitter, and they'll only be activated if the PLC fails, and then it'll switch to float control because it's constantly monitoring the PLC, and the float control will take over and run the pumps in the station until the PLC is back online. In the next cabinet, we have the pump terminal box. The pump terminal box is where you'll do all the pump checks from. So one of the first things we do, if we have let's just say we had a trip breaker, we don't just reset the breaker, because a trip breaker is pretty serious. Something bad had to happen to trip a breaker. So one of the first things we're going to do is disconnect the motor straight from the pump cable to the pump terminal box. We're going to disconnect those 3 lines, and we're going to meg it to make sure there's not a direct ground fault in the motor, so that we don't hurt somebody when we reset that breaker. Of course, before we do this, the breakers are off. This pump's turned off just like we did when we pulled it. And to be extra safe, we even check the voltage. When you're working on pumps with VFDs, there could be voltage even after you turn everything off, until the bleed resistors in the VFD completely get rid of all the voltage. Okay, so now we're going to take the megger, connect one lead to the line and another lead to ground, and we're looking for any fault to ground, which would tell us not to reset that breaker. First, we're going to make sure it works.
I got it here.
No resistance to ground. All right, from one line.
I got it.
Oh, he's got the test button on his lead. Okay, so line 1 is over 550 megohms to ground, so it's good. Line 2 is also 550 megohms to ground, and line 3 is 550 megohms to ground. The voltage we used was 525 volts DC, and that's a safety measure. We could do it at 1,000, but just in case we did not disconnect from a soft start or a VFD using 525 volts prevents us from doing any serious damage to any components in the panel. And now we'll reconnect the leads, and then we'll check the sensor leads over here. All right, in addition to the motor power leads, there's also a control lead. The control lead has 4 wires in it. 2 wires are used for the thermals, and the other wires are used for communication to a pump sensor monitoring device that's in the top of the pump, in that terminal box in the pump. It's called the pump electronic module, and it talks digital communication over wires 1 and 2 to the base unit that's inside the control panel. And we'll go over that in a little bit. But we're not going to check 1 and 2 because it's very high ohm. It's anywhere from 40 to 80 to 100 and something ohms, depending on what state it's in. But T3 and 4 should be somewhere less than 3 ohms. So we're going to check that real quick. Okay, he's reading continuity at 1.7 ohms. So T3 and T4 are good, so we'll put them back in service. It doesn't matter which direction you put it. 3 can go on 4 and 4 can go on 3 because it's a resistive circuit. It's not polarity. There's no polarity. For T1 and 2, there is polarity, so if you disconnect it, you have to put it back exactly the way you took it off. We're at the level transmitter, which is the PLC's primary means for turning the pumps on and off at the prescribed levels. So it uses this device with a sealed connected cable going down to a pressure transmitter. That pressure transmitter senses the weight of the water or the pressure above the sensor, and then that pressure is converted to a 4 to 20 signal, and then you can use the settings on these buttons here to scale it. It's scaled based on the level and the controls that they're going to use in the PLC. And whatever scale that's in here has to match the scale in the PLC or vice versa. It only uses a shielded cable to communicate from here. It transmits from here to the PLC, and the PLC reads that difference. It's an aluminum cover. It unscrews. If it's too tight, you can use a screwdriver across these to loosen it. Making connections, you grab the top and the bottom and you pull it out, and there's the 2 wires right here that are used for communication, and then it has dip switches based on whether you're using current or voltage, and you can also zero the meter out or respan it based on its current connection. But you do have to take this off to operate the menu buttons. We're on the force main after it leaves the valve vault, and in this vault there's a pressure transmitter and a flow meter. From here we're taking 4 to 20 signals, and we're reading the pressure in the force main, which is going to be a little bit less than the pressure that the pumps see because the pumps are lower than this pipe. So when they look at the pressure on the force main, it's not the discharge pressure of the pumps. The discharge pressure of the pumps includes all the resistance going through these pipes, plus the check valves and the plug valve, and the distance down and the head elevation difference going down to the pump. From this flow meter, it goes back to the PLC. The PLC displays pressure or flow, and as it detects the magnetic disturbance of the flow going through the Krone flow meter, and estimates the velocity of the fluid and the cross-sectional area to determine the flow rate. The pressure transmitter just looks at the pressure in the force main, and together with the flow you can get an idea of the performance of the pumps as well as the condition of the force main. for instance, when the pumps are all off, that pressure should stay the same all the time. If you get lower pressure when the pumps are off, then that could indicate a problem on the force main with the possible leak or something worse happening like a break. But it could also help you with a faulty air release valve. If the static pressure starts getting higher and higher, that could indicate that an air release valve has stopped working and is increasing the resting pressure when the pump is running, or it could just be a closed valve. A lot of time when the pump is running and the pressure keeps getting higher and higher, that usually indicates a pressure valve or a air release valve failure as well. Looking down in the vault, the light blue item is the pressure transmitter, and it's hooked directly to the PLC cabinet for the PLC to read the pressure. And then this gray item in the pipe is the flow meter. And you'll notice the copper wire connected on both sides. The flow meter is highly dependent on a ground. And you notice that the ground is not connected in the conduit or anything like that. This is an earth ground. So that earth ground needs to be checked and maintained over the life of this flow meter for it to be accurate and for it to last. And it has grounding rings, but this ground is a backup to the grounding rings in case of corrosion and things like that. The earth ground is in this box right here, and it's a ground rod that's driven down into the earth as a ground reference backup for that flow meter. We're in the valve vault that all three pumps pump through. There's an air release valve on each one, which is piped back into the wet well. As the pumps turn on, these air release valves open, allowing this line to empty before it gets to the check valve. And then when the pumps turn off, and this is really important, these air release valves open up and allow air back in so that you don't get a vacuum condition behind this check valve. That helps the check valve last longer, and it also is better for the pipe, and it prevents the check valve flapper from slamming really hard as well. The check valve the main purpose of that is it closes after the pump is done pumping so that the force main pressure doesn't come back and dump into the wet well. And also, if there's multiple pumps running and one should be a higher pressure than the other for whatever reason, the check valve will close and not allow it to pump back through the other pump. All these pumps pump around the same, so they'll just both open together and they'll pump even more when two pumps are running. These pressure gauges are used so that we can look at the pressure while the pumps are running. And the plug valves are used so that you can isolate each pump for maintenance or for working on the check valve or the pressure or the air release valve or changing out the pressure gauge. In this case, they have individual valves on them, so hopefully you wouldn't have to replace the saddle. Okay, we're at CP100, which is the pump control panel. This door will stay closed until you open up the main, and it does not have a dead front on it. It's got the safety and arc flash information on this door. It says 1.93 calories per centimeter squared, so 4-foot arc flash boundary. So if you're doing hot work in here, which you shouldn't be doing, you would have to cordon off a 4-foot area so other people couldn't be around while you're doing the hot work. Of course, you have to have the appropriate PPE as well. For what we're doing, a level 1 PPE is fine, which is fire rated shirt, pants, and I also have a fire rated face shield as well, but I'm not going to put it on so that you can actually hear me while I'm talking. But normally my helmet would have a shield on it as well. And then I'd be using fire rated electrical gloves rated for at least 1,000 volt, and then a cover on them to protect them as well. Going over the panel, the colored wires are your main power coming in from the service disconnect. The service disconnect is right next to the transfer switch, and they'll go over that in the generator video, so we're not going to cover that here. From the service disconnect, we go to this main breaker. It's a 600 amp main breaker, and it's got all sorts of settings on it based on how much the current has to go up before it'll trip, how long it'll take, and that sort of thing. Then it gets distributed in these terminals to various pump breakers, grinder breakers, valve breakers. So those all those motorized valves and the grinders are all run from these breakers over here. The main breakers, these three breakers are for the pumps 1, 2, and 3. They're 150 amp for 125 amp pumps. Then you have reduced voltage soft starts, which slowly start the pumps. I think they're set for 10-second ramp and 10-second ramp down after they turn off. They're all set for 125 full load amps and 400% of full load amps for starting. So if it's 125 amps, they should be drawing no more than 500 amps during a startup procedure based on the settings in the ATS-22. The ATS-22 model soft start has a built-in bypass contactor. So after it completes its soft start, it'll close the bypass contactor and run 100% voltage down to the pump until it's ready to turn off, at which point it opens the bypass contactor and does its reduced voltage soft stop. Coming from the soft start, it goes directly to the pumps through those terminal cabinets we looked at earlier. Each one of these pumps has a CT on it, which monitors the current, and that current is sent back to the PLC, which we'll go over last, and they're able to look at the current when the pump runs coming off the soft start. On the side here, there's two small motor contactors. Those are the motor contactors that are connected to those 480 volt plugs we talked about at the storage tank. So when you turn that switch to on, it closes these motor contactors and allows the fans that you have connected to them to turn on. The switch to turn on those fans is over at those plugs, so that the person operating it can see the position of the switch and tell whether it's on or not before they plug into it. Each one of these has its own breaker, so if they had to do any work on that circuit, they could de-energize the breaker prior to doing the work. Up here in the upper corner, you have a control power transformer. This control power transformer is for this control panel, as well as the PLC control panel. There's three-phase fuses here that go to our phase monitor. A green light, steady, is normal. If it's flashing, it's in the process of starting. If it turns red and is solid, that means the phases are reversed. If it turns red and flashes, you either have phase loss or a low voltage condition. This is our surge protector. The surge protector for this panel only. There's a separate surge protector for the station, which is not supplied. Well, actually it is supplied by us. So the surge suppressor is located right next to the main circuit breaker. And what it does is it gets rid of all the high voltage transients up the line and protects all the equipment at the station. That smaller surge suppressor is just for that cabinet. So this one actually protects everything here, and then there's another one in the cabinet for the controls for that cabinet. And like I was talking about earlier, the main circuit breaker goes to the transfer switch. From the transfer switch, everything goes to the control panels, and then from the control panels it goes out to all the different devices. The reason it goes to the transfer switch first is because if there's a power loss, then the transfer switch will connect to the generator and that way everything is still connected to power as it switches from one to the other. If we came straight off the breaker, then when the transfer switch switched, nothing would be connected to the generator. So we connect to the transfer switch first, and then the generator is connected to the other side of the transfer switch, and then the load is connected and it switches between the main circuit breaker and the generator. All right, we'll move over to the next other half of that panel now. All right, so for the CP100 on the control side of the panel, we have what's called a dead front, and the dead front has all the operator controls on it. The top is the monitoring status panel that looks at all the sensors on the pump. Right now it's showing everything okay, no problems. Then you have a power okay indication light, which must be burned out, by the way, because I can tell there's power, but that light's not on. It should be on. And then you've got 3 elapsed time meters, 1 for each motor, all of them showing about 7 hours apiece. Then you have the handoff auto operation for each pump. Unlike other places, these will start running the second you put them in hand, as long as the PLC is not in operation. If the PLC is in operation, then it may prevent you from running these in hand. And I'll demonstrate. So if I put this in hand, nothing happens because the PLC holds out the, oh wait. So okay, that's not the case here then.
What's that? Most of them, the hand overrides it.
All right. Well, in some places the PLC holds that out too, but in any case, the only thing that's held out then is the float controls. So some of the older stations, the hand off auto switch is also held out, but in this case it's only the float controls. So you can run these in hand when you turn it to hand, and when it's in auto, it's in PLC control. If you get a fault from any one of these sensors or from the over temp sensor, it'll light up the pump fault light, and you can reset it directly from here. It'll also tell you if it's switched over to flow control, so if the PLC fails, this light will come on, and that light actually works. So you can press these lights to test them and see if the bulb's good. This one doesn't come on, so that's how I know the bulb is bad. So we need a bulb for that one. And then this is the Mission RTU. The Mission RTU is very simple. It pretty much is just used for power fail and high level. So they don't usually connect anything else. They might connect generator run to it sometime, but for the most place it's just generator, high level, and power fail. We open up the cabinet. Here's all your control breakers that distribute the power throughout the various panels, including the PLC panel. You can turn off the PLC panel from over here. There's a set of wiring diagrams inside the PLC panel for this panel and for that panel if you want to go over the specific circuits that do specific things. This is a 24-volt power supply. Right next to it is a breaker for the 24-volt DC power supply. These are the DC fuses. So for the various items that are powered by 24-volt DC, they each have a fuse. This is the motor protection system. This right here talks to all 3 of the pump's motor protection units, the base units, and then it transmits that information to this screen where you can see the status of the pumps. Here's some more fuses, both for 120 and actually these are relays, I'm sorry. These are single pole relays for various conditions coming off of the base unit and the motor protection relays. Then we have separate relays for various control functions, time delays for starting the pump and for faults. And then we have what we just added, which is in the newest set of drawings. This is your fan control circuit. it has the fuse going out to the fan switch, and then the connections for the 120 volt control for the motor contactors we looked at there. This is for the mission unit. It's not used, but it's additional I/O if they wanted to add other things to the mission unit. And then down at the bottom is this is where you could plug in a laptop if you wanted to connect to the motor protection system and do programming with the laptop. You can, but you can also program through here, so it's not necessary. And then this is a heater to make sure we don't get in a condensation condition below 40 degrees inside the panel. This is the power supply for the mission unit. It's 12 volt DC, class 2 transformer, 20 volt amp. And this is a little battery for the mission unit, so if everything else loses power, the mission unit can still monitor that high level float and tell them if there's a high level and call them on a separate system altogether as a backup. Okay, now we'll go over this. This is the display screen for the MOS 801 system. They have 3 pumps here, and as you can see right now, the little green arrow on one is indicating that this pump is running. It's drawing 107.2 amps. Its stator temperature is 112 degrees, the main bearing is at 82 degrees, and there's little to no vibration, 0.087 millimeters per second. So that's, as these run, we'll get trends for them, and we'll adjust alarm levels according to how they run. But that's not something we're going to show you in this class. That's something we do as a maintenance item when we come do our annual inspections. On the main screen, all the pumps display their current, stator temperature, main bearing, and vibration. And as long as all those are normal, you won't have any alarm, but you'll get used to seeing what they normally run at, and they should run fairly close to each other. On this upper button here, the pump station button, you have the status, which is the screen we looked at, and you have the active alarms, which right now there are no active alarms for any of the pumps or the system. And then you have an alarm and event log, so if you wanted to go back in time and look at what happened at whatever time, you could go back through here and you can filter them and read and look at the different alarms that happened over time. The next screen is the data button. For here you can look at graphs, and you can select a particular item, or you can go back to the status page and click on that item and pull up the graph from there, and I'll demonstrate that. So if I go to the status screen and I click on any one of these pumps, I've got pump 1, and it has the data plate information. So the same information was on that data plate we looked at when the pump was pulled is displayed here. And then it also has the start and stop log. So you can see all the starts and stop, how long it ran. And I'm going to close these as I go so it doesn't get too busy. Then you have the various channels that look at the different sensors. So we'll look at runtime and starts first. And it says that the pump is currently off, but you can look at a graph of it if you want and see when it ran. So now we pulled up the graph and you can see when it ran last. This is in seconds, so it's not a very large scale. You can scale it to minutes, hours, and days to get a larger scale. And we'll go back to pump station, status, go back to pump 1, and then we'll go back to runtime and starts. In runtime and starts, you can look at the duty rate in a 24-hour period. Each one of these pumps runs about 8% of the day. So it's very underloaded right now. and then the pump duty rate in a 7-day average is at 6%. So, and they should be fairly close. Runtime total is 76 hours, or I'm sorry, yeah, 76 hours with a total of 1,315 starts, and we're starting per hour is 1.4 starts per hour and about 26 starts per day. And then you could go to each pump and look at that. You can look at the individual sensor information. So I got the stator housing leakage sensor is at 10.1 milliamps, and the junction box leakage sensor is at 8 milliamps. That's pretty standard. It shouldn't vary from that at all. They're two different types of sensors. The temperature sensors, these will vary. So if you want to look at a graph, it's a lot better to look at a temperature sensor graph because you'll actually see some change. So if we look at, let's just say the main bearing, right? If we look at the main bearing and pull up the graph for it, we'll actually see something on it once it loads. Not much. It's not too much temperature variation, but you can see that it varies over time. And you can rescale this, which is, and again, something you can do during a maintenance period, is you could come and rescale these graphs and then set, see right now the alarm is set way up at 240 some odd degrees, and the warning is set at 194. Well, over time we'll see how these run, and if they never get anywhere close to that, we'll lower the warning down to closer to where it actually runs, so that when it gets outside of its normal running condition, we'll get an alarm earlier than waiting till it's way outside its normal running condition and doing extreme damage. Now, if it ran up there all the time, then there'd be no reason to change it and it'd be fine. But if something happened that was outside of normal for this application, then it could be doing damage and we'd have no idea. So it's always best to look at how your pump runs. So if you have the ability to look at a trend, look how it runs, you should adjust your warning levels to just outside the normal operating area. And of course, you want to make sure you check storms and stuff like that. We usually say wait 6 months. So after 6 months, you should have a good idea of how it's going to run and what the extremes are. And it tracks them, you know, so it'll tell you what the highest value it got was. And you'll be able to say, okay, well, if that was an extreme condition or something bad happened, then maybe I want to adjust it down so it trips before that happens again. So we'll go back to status. And we'll go back to the pump again. And we'll go look at the channels. And this time we'll look at, I do want to go with temperature and just show you that. So this was, actually it just shows actual high and very high. On the graph is where it shows what its highest was. But this one shows what its actual temperature is versus its trip temperatures. It also does histographs, but honestly, I have no idea how to use those, so I always go to the regular graph. Vibration. Let's close these. It's a 3-axis vibration, so it has the, I'm sorry, this is still temperature. Vibration. Yep, there we go. You have X, Y, and Z axis vibration. This thing barely registers any vibration, so you won't ever see anything on this graph. But I'll pull one up anyway. Usually the worst one is the X one, so I'm going to pull that one up. And yeah, there's a little bit. You can see it a little bit, but the trip level is way up there, so not even close. So, but anyway, it's a good thing to compare with your running graph to see what the vibration and the amps are, because you can also pull up amps here too. On all of these, you can add other channels to what you're looking at on that graph from the graph screen. Vibration, electrical. Yeah, the electrical is where the pump current is and the frequency is. So it'll show you both the current and the frequency that the pump is running at, which is useful if you're working on a VFD to make sure that the VFD frequency of what you think you're putting out is what you're actually getting. And I haven't seen where that hasn't been the case yet, but I have heard of instances where that does sometimes happen. But pump current, if we pull that up, it should show similar to what the vibration did to match the run time. Give it time to load there. And yeah, you can see that the pump current, what is it set at? Yeah, you can see it spikes when it starts, and it should spike when it starts because it'll draw up to 4 times the full load amps. So it's going to go over that, but it has to stay there for over 10 seconds to trip it. So this thing is set for whatever the time delay is on the starter for ramping up. The time delay for it to trip on current is set to the same so that it doesn't trip every time you start it. These draw, when they run, they draw about 107 amps. Well, full load is 125, so that's really close. So we won't be changing these alarms. They'll stay where they're at. It has service intervals, but those are turned off because these pumps are serviced every year. So we left that off so it doesn't give aggravating alarms for no reason. We have settings. You have to put in a code to change the settings. John told me not to do those, so I'm not going to do that in this video. And reminders, that's if you ever have to change a base unit or a component like the PEM, it's going to give you a reminder to actually install that. That would be under settings and programming, so that's going to be a separate class that we'll do just for the MOS 801 system. That's not something you'd be doing here in the field as an operator. And then last is help. Under help, it'll give you ideas for if you get an alarm on a certain item. It'll tell you the different things that could cause that. It'll not only show up here, but it'll show up on the alarm itself. It'll give you a little information button you can press to bring up the alarm information. If you go to upgrade, again, that's something for another class that's done from here as well. And so that's the basic overview of the MOS 801 system. To reset it, you'll have to acknowledge the alarm. You'll press a button, and we'll go over that. And then it'll ask you to enter your initials. If you don't, it'll still let you do it anyway. And then you'll have to reset it, and then if it's resettable, it'll go back to normal once you do that. All right, we'll go on to the demo unit so that I can demonstrate a failure and resetting.
This is a MOS demo unit, and it's got everything all in one spot. This is your PEM unit. This is what's actually in your pump top. So all your sensors are hooked up down here, and then you have your T1 and T2 that goes back to your panel connected here. That'll go all the way to your base unit right here. Your base unit is pump specific. So each pump will have its own base unit, and it talks to the central unit, which is also in your panel. This is your power analyzer. This reads the power coming in and makes sure everything looks good there. And so on this demo unit, we have different current switches, voltage switches. I can open a thermal contact. I've got an FLS as the float sensor. So it's got a few different things that you can trigger. So what I'm going to do is trigger a thermal contact by opening this. This is simulating if your pump was to overheat, that thermal contact will open up, and in just a second it'll register, and it did. So now on our base unit we have an A alarm, which has your pump locked out. If you look on your screen, you've got a red bar here. So I want to know what that alarm is. As an operator, I come to the screen, I have an alarm, let's see what it is. I go to pump station, and then I'm going to click active alarms. So I've simulated a thermal contact opening, meaning the pump has overheated. And so I come to the panel, and I see I have a red line on pump 1 and also a red light on my base unit. So I'm going to click pump station. I'm going to go to active alarms. When it pulls up, it says temperature thermal contact status very high. So that tells me what my alarm is. So I'm going to reset the thermal contact. So if the pump were to reset itself, cool down. And now I have no active alarms here, but it's still showing a blinking red light because it needs to be acknowledged. I'm going to press acknowledge all, and then it says there's no active alarms because there's no longer a fault. So click acknowledge all. It will go through and acknowledge everything from the CU, the BU, and the PIM. Once that's done, I can click close, and now our A alarm is no longer blinking. So I can go back to pump station, status, and we no longer have a red bar. And if you look at the base unit, there's no longer an alarm light, but you've got a green go light, meaning the base unit is happy and it'll allow the pump to run.
Okay, the last thing on our schedule today is control panel 101, the PLC control panel. It's a 120 volt control panel. It gets all of its power from CP100, the pump control panel. Its power distribution is these breakers here and these breakers here, as well as these breakers over here. On the top you have the PLC, which basically runs everything and is reading all the various sensors throughout the station, all the pressure level, the current sensors, anything coming from the generator, the grinders, the pumps, the pump control panel. It controls turning the lights on and off. It looks at the flow meter, the pressure transmitter. It even looks at whether this switch is open or closed. So right now they know I'm in their cabinet. The PLC has two 24 volt DC power supplies, Ethernet switch which is managed, so it's protected, it's on their county network. You can't just hook up to it and hook up your laptop and start checking stuff out on their network. It won't let you do it. This is their modem. It's a cellular network, so this is how they actually get on the network, through their cellular antenna. The various sensors come in through this terminal strip here. The isolated one is for the level transmitter because it comes from the wet well, so it goes through this isolation barrier first before it gets into the controls. The power supply for this whole cabinet is backed up by this UPS with two backup batteries. This is the latest version of the Phoenix Contact UPS, and it's probably what you'll start seeing in the Gwinnett County cabinets moving forward because the old Allen Bradley one isn't available anymore. I'm sure they came out with a new one, but they didn't come out with a new one in time for us to do this panel. The control relays that the PLC uses are here, and the various fuses for all of the sensors leaving this cabinet are over here and over here and over here. Every sensor lead has a fuse on it, so if anything happens in the field through the field conduit, it blows the fuse and doesn't take out the PLC. All right, this is the main PLC control screen. I'm going to go over some of the basic functions on it. There's other classes that they do in-house for the more involved things you can do from this screen. The first thing you notice that is it displays the level. Right now it's reading 5.5 feet and it's scaled to 34.5 feet. So if you wanted to know what the scale was, you could always come over here at 0 to 34.5. So on my level transmitter, I want to make sure it's scaled 0 to 34.5. The levels to actually run and turn things off, the first one's the stop level is 4.5 feet. The first stop is 5.5, so that's a lag stop. And then if there's 3 pumps running, it'll stop at 6.5. Lead start is at 9.5. The 2 pump running start is at 10.5 feet, and 3 pump running start is at 11.5 feet. There should never be a condition where there's 3 pumps running, but in case they need it, it will turn on. On here you see the conditions of the float. Right now the off float is underwater, and it's above 5.5 or 4.5, so it should be underwater. And then the lead float is not underwater, but it probably won't go underwater until you see lead start. And then you've got the lag and high level floats. Those floats are monitored even though they're not active, and so that they can tell if the float stopped working before they need it. So if they'll get an alarm if they don't see a float come on before they get their lead, before they issue their lead command based on the level transmitter level. Next you can see the status of the pumps. Right now they're all in auto and remote, and when they run they'll change their thing to run, and you'll be able to see the amps when you go on each individual screen. It'll tell you if it's on backup control running off of floats. It'll tell you what the discharge pressure is. Right now the discharge pressure at that vault right now is at 30, somewhere around 38 psi, and again that's above the pumps, so you have to add the amount of feet going down to the pumps to get the actual discharge pressure from the pump. So that's the discharge pressure from the pressure sensor in the vault. It's tracking the flow. Yesterday it pumped about almost 6.679 million gallons, and today it's pumped almost 0.2 million gallons so far. The high level alarms are over here, and you can see that grinder 1 is running and in remote, and grinder 2 is stopped and also in remote. And like I said before, they only need 1 grinder, so they run 1 and then switch to the other and go back and forth. Right now they've got the valve or the gate closed on the other grinder, so it's not running at all, but it won't get all full of trash because they closed the gate, so it'll be able to run when they need it. They'll still come out and maintenance run it, because you can't leave grinders not running for long periods of time, otherwise they'll lock up. If you want to look at a specific pump, you can go to like pump 1 and you can put it in hand, or you can turn it off and take it out of service. So if I turn it off and I take it out of service, it's going to change what it looks like to that, and it'll also look like that on the home screen, so you can see it's out of service. So when I put it back in auto, well, first I got to put it in service. When I put it back in auto, then it'll go back to its normal appearance. And when it runs, let's see what level it's at, 7.4. It's still got a couple of feet to run, so I'll just put 1 in hand. When it runs, it's going to change its status, and from this screen you can actually see the amps. Right, it jumped up to 200 when it started, but it'll go back down once it gets going. And once it gets up to pressure, it should run a little over 100. And if you go to the home screen, you won't see the amps, but you'll be able to tell that it's running and that it's in hand by the little screen running on that. And let me put it back in auto. They have little mass data screen for these pumps as well. So you can from here take a look at the various MOS sensors, because they're talking Modbus to our CU unit and getting those values back here, but probably better to go directly to the MOS unit to get that information. But if you wanted to look at it all at once, it's right here. And that's it for this level of control that we're going to do for this video.
Yes, my name is Rory Russo with Hayward Incorporated Atlanta. We're the local representative for JWC Environmental. They make the Muffin Monster and Channel Monster grinders. Here at this station we have two very large Channel Monsters that are in the bottom of this pump station. Prior to the pumps, they grind up the solids to protect the pumps so they don't clog up with various sundry solids that the public pump flushes down the toilet. So with that said, the grinders run continuously regardless of when the pumps are running, so they'll run 24/7. They have the ability with this system to interlock the pumps with the grinders if they want to run when the pumps run, or when they want to run when there's flow or not flow coming into the station. Typically most of the stations run the grinders continuously on a 24-hour basis, 24/7, 365. The control panels are pretty simplistic. There's a PLC system built into the control panel that operates and monitors the grinders for status, run status, overload status, fault status, and that all is linked back into the SCADA system for the county. So if in the event there's a failure, it'll alarm and tell the county's personnel that there's a fault issue, and they'll come over here and check it out. Typically these things run for about 3 to 5 years depending on the amount of grit that comes through the station, and once at the 3 to 5 year mark they'll start to wear out, and they'll go into a service mode, and we'll replace the wear parts, and then they'll put them back to like new conditions. If in the event there's a problem with these units, there's two ways. You could either call us at Hayward Incorporated, who's a local representative. My phone number is 404-444-0026. That's 404-444-0026, and my name is Roy Russo, and I'm with Hayward Incorporated. Or you could call the Parts and Service Department that's on inside face of each panel. The number is 800-331-2277, and call those gentlemen. The good news for JWC Environmental, the service manager and probably half of the service staff for the whole North America is here in Atlanta. So getting a service guy out here quickly is easy and convenient, and normally without pain to get somebody out here to help and support the county. With that said, it's a very simple system. It runs on its own. It runs continuously. It runs for 3 to 5 years until it wears out. And the control panels are pretty simplistic. They're integrated with a PLC system into the plant or the county's SCADA system for reporting status, run status, fault status, and any overload statuses, be it motor overload, jam overload, as you see here, or a power problem. The system will theoretically, when the power shuts off and goes into emergency mode, which should automatically restart itself, just like the pumps, and the system continues to run in the event of a power outage. And when the power is transferred back over to mainline power, it'll automatically accommodate that change in power supply also. So with that said, it's a very simple system. All the controls are supplied by JWC. All the control panel drawings are within the panels. Each panel has a set of control drawings. Also has all the serial numbers and all the status. If in the event there's something wrong with it, they could call that number or call me, give us a serial number. We could research internally the details of it and provide assistance, and or bring somebody out here who could help solve if in the event there's a problem. These things are pretty robust. I would say rarely do you have a problem once they're started up and we get all the electrical kinks worked out. And mainly, normally, they're control issues, getting all the various control logics to talk to themselves. But once we're past all that, usually these things run on a continuous basis without issue. Once again, thank you very much. We appreciate your business. My name is Roy Russo again with Hayward Incorporated to talk about the JWC Channel Monster grinders at the Little Suwannee River Pump Station. We're here in front of the hatch where the grinders are. They're 2 stories down in the channels. They're running. The grinders consist of the grinder itself, the channel frame assembly, and the rail assembly. So when you want to inspect the grinders, you will hook a chain and a crane to the support structure that's on the grinder itself and rail the unit up the rail system to the top here, so you can inspect it in a safe environment, unencumbered by the H2S gases that accumulate down in the pump station. So for safety purposes, the units that are down there have immersible motors that are explosion proof to prevent any of the gases from creating any potential volatile environments. Other than that, the basic thing is not to go down there without oxygen protection, without pure ox systems to keep you safe, and to rail the units up to the top so you could inspect them on a probably once every 6-month basis. Once again, if you have any questions, you could always call me at Hayward Incorporated at 404-444-0026, or call JWC at 1-800-331-2277. If you have any questions, thank you. This is Roy Russo. Bye now.
Jacob Garcia with Golden Harvest, here to just demonstrate what we have here at this pump station. Operating a Rotork gearbox, a Rotork EMO actuator for the slide gates down below. So what you see here is you have your stem cover, monitoring your stem. If you have to run this thing manually, you can run it manually by engaging this lever here. And what you want to do is you want to hold this down, wait till it engages, and then to move it back and forth. So if you're going open or close. So once this thing is engaged, you can let go of the lever and it should still be engaged. Also too, if you needed to run it in manual mode, this is your manual operation. If you want to run it here locally, there's these 3 levels here. This is your local operation, this is your stop, and this is your remote. So what we're gonna do is we're gonna run it in local, which is meaning that I can have the operations done here, open and close. This being open, this one meaning close. So we're gonna go ahead and open this one. Also, with that being said, this will give you your percentages. Percentages indicate how far along it is all the way open and all the way closed. 100% is open, 0% is closed, fully closed.